Welcome, everyone. We are just about to get started in this month's technical webinar, but let's give folks just a minute or so to join in. I see quite a few folks are just now logging in, so just give us another 30 seconds or a minute, and we'll go ahead and get started. This is actually a very exciting week for IWCS. We are actually a week away from the deadline for receiving technical paper abstracts for this year's 75th anniversary conference. So if you haven't already, please consider submitting an abstract. It's a very simple process, and I think you'll find it's going to be an excellent conference to celebrate our 75th anniversary. So more on that later. Okay, well, why don't we go ahead and get started? And again, welcome from wherever you are. We actually have attendees from all over. So some are late into the evening, and we thank you for that. We hope you have a glass of wine or a beer or something and enjoy your evening. But good morning, good afternoon, good evening. My name is Dave Cadu, and I'm honored to be the CEO and director of IWCS, and I'll be your host for today's webinar. We have a few housekeeping items. Um, so you know, as an attendee, you're part of a larger audience. So during the presentation, all participants will remain in listen-only mode, and this event is being recorded, so you can go back and watch it again or share it with your colleagues. The links are available from our website as well as on our YouTube channel. We encourage you to submit written questions. That is in the chat function. So if you open up the chat, you can enter your questions. It should be on the right of your screen, and then hit the send button. Your questions will be addressed at the end of the presentation, time permitting. Today, our technical paper webinar is hosted by the IWCS Cable and Connectivity Industry Forum, and we offer a series of webinars on important trends and technologies for the perspectives of our supply chain leaders and sponsors, and also the outstanding papers from our last conference in Pittsburgh last October. Today, we're honored and welcome Huimen Chao from Covestro. She's located in Illinois, USA. Dr. Chao will present her paper on the Kinetic study on next generation optical fiber coatings with improved processing robustness. Dr. Chao is a science fellow at the Science and Technology Group at Covestro, and her expertise is material science with a focus on materials properties and structure property relationships. So Huimen, thank you so much again for continuing to provide excellent content to IWCS. And go ahead and take it away.
All right. Thank you, David, and thank you to IWCS giving us this additional opportunity. And I, as the speaker representing my co-authors, Guido Hansen and Grant Sheridan, representing Covestro Fiber Optics Material Group, presenting this IWCS paper again to a broader audience. And this paper was originally presented at the session of fiber manufacturing, not the material session as usual. And that was indeed a perfect fit for this paper because the kinetic behavior of the UV curable coating plays major role impacting the robustness of the fiber drawing process. It is one thing for us as a coating supplier and reporting the coating properties usually as a cured coating film, but ultimately what matters the most is how well the design properties of the coating can be robustly achieved on fiber. And this on-fiber property building strongly depends on how the reaction kinetics of the coating responds to the actual fiber drawing conditions. And I will explain how our new generation coating designed with a very unique kinetic behavior will further improve the optical fiber processing robustness. And because we have some more time today for this webinar, before I go into detailed discussions, here I added a general overview of our main research and development efforts in recent years. In Covestro Fiber Optic Materials Group, previously as DSM Desotech, in our 40 plus years of a history supporting the optical fiber industry, never stopped innovation efforts. And these efforts are always driven by customer and industry needs. And one ever-increasing need from fiber manufacturers is increased production efficiency. Faster and faster draw speed becomes more and more demanding on coating cure speed. Helium saving, uh, which means our coating now needs to support hotter and hotter glass on both rheology and cure speed point of view. UV LED cure as the major trend. The first paper in IWCS 10 years ago comprehensively discussing UV LED curable coating performance on fiber was from us. And among all processing related topics, processing robustness is a constant theme, which is what this paper is focusing on. It is about how our coating, despite the possible different settings in your processing window, still able to achieve stable properties and support robust fiber performance. And this is truly value added to the to the fiber manufacturers, giving them more freedom adjusting their conditions according to their own needs. And for enhancing fiber performance, we have been making continuous progress, keep reducing microbending sensitivity of the dual layer coating system, which is highly desirable for supporting the trend of reduced diameter fibers and for the fiber types of high microbending sensitivity, such as the large effective area fibers, or simply for supporting the ultra high density cable where the stress exerted on fiber is higher and higher. And then the directly relevant to the ultra-low microbending design, we emphasize from very early on, it is very critical to mitigate the risk of ultra-soft primary coating defect formation, such as delamination and cavitation under external impact, such as in proof test. And the first paper at IWCS discussing high cavitation strength soft primary coating was our 2006 paper. And now, 20 years later, our new generation coating is truly demonstrating this ideal combination of superior microbending performance combined with robust mechanical protection against defects such as cavitation. And last but not the least, the reliable field performance, ensuring long-term durability at a broad range of field conditions. And there are many more detailed customer voices besides these key topics that we also take into account when we set design criteria for our new generation coatings. And this is why we identify ourselves as the solution provider to meet the challenging needs of optical fiber industry, and will always be willing to listen to customer voices. We published our first Kinetic paper in 2020, introduced a very valuable tool using a draw tower simulator to capture coating cure in a full set of UV doses in order to fit into a reaction kinetic curve. And from those fitted curves, we can obtain the reaction constant for double bond conversion, so-called Kc, C means conversion, and as well as modulus buildup reaction constant, Ke, E as in the terms of elastic modulus. And in this study, we introduced this new parameter Ke over Kc ratio, and I will explain why all conventional coatings, regardless fast or slow cure, this ratio is always less than 1, which means modulus buildup is slower than conversion. But our new generation coating starts to show a breakthrough behavior of Ke over Kc ratio equals to or even higher than 1, which you will see how this feature greatly improves the processing robustness. And we did some mechanism study and proposed possible attributes why this unconventional kinetic behavior became possible with our new generation coating. And at the end of the day, what makes this feature interesting in technical sense is all because of its value in making fiber drawing process more robust, which you will see at the end of the talk, the proof of actual glass fiber drawing results comparing both conventional and new generation coatings. And here's a quick overview of acrylic coating free radical photopolymerization reactions through initiation and propagation. And this is the main process where the chain grows and cross-linking network forms. And in the end, termination of radicals. The monitoring of double bond conversion through real-time FTIR or near IR gives this type of kinetic curves. And this curve fits very well into a pseudo first-order kinetic curve. And here's the first-order reaction equation used to fit this curve. You can see this is a perfect fit. The pseudo first-order model is not just empirical. It is actually well-founded by theoretical kinetic models, such as this most commonly used reaction diffusion model. And this model assumes steady-state propagation process where all these parameters are all constants, which are combined into one overall rate constant K. And for double bond conversion, this would be Kc. And for modulus buildup, this it also follows the first order kinetic curve, which you can see here is the real-time DMA. The experimental and the fitted curve fits perfectly well, and the Ke is the reaction rate constant. And it should be noted that the Ke and the Kc are typically not equal to each other. T0 is the induction time where this curve started to rise. And T0E is always longer than T0C because it takes time for the reaction passing the gel time, turning from liquid to solid when elastic modulus starts to be measurable. Here is to describe again our methodology introduced in our 2020 paper using the draw tower simulator, drawing a stainless steel wire fiber with the same coating process as the actual fiber drawing, wet on wet or wet on dry, microwave or LED lamp, and with the draw speed setting up to 3,500 meters per minute. Very impressive. And for kinetic study, we would set the draw speed and lamps numbers to a series of low to high exposure times in order to capture a complete reaction process. And we measure the cure degree from the double bond conversion at the inner surface of the primary coating represented by percent RAU, which means reacted acrylate unsaturation, and as well as primary in situ modulus, we call it primary ISM, in situ modulus, and it's described in more detail in our 2003 paper, which you can take reference to. In our 2020 paper, we were showing 3 coatings, A, B, and C from cure speed, from slow to fast, not only a conversion from slow to fast, and especially in modulus buildup. This is A, B, C from slow to fast. And when plotting these into a ISM versus RU curve, it shows A being the sharpest rising of modulus at the last stage of conversion, and C is much more flat. But in terms of the shape of the curve, they all share the same feature, which is categorized as the accelerated increasing shape. And that means the rise of modulus gets sharper and sharper at the last stage of the conversion. And this is the feature making the coating property very sensitive to the processing condition, even when you thought it cured very well, reaching 90% of the cure degree. And the sensitivity of modulus rising is actually the highest in the last 10% of the cure. For example, the coating A at 80% of the conversion is only reaching 25% of the modulus, and then 90% of the conversion still only about 50% of the modulus buildup. And these may lead to a wide scattering of your coated fiber primary coating modulus, even with minor cure degree variations. And this shape of ISM versus RU curve is solely determined by this Ke over Kc ratio. And all the conventional coatings have Ke over Kc less than 1. Even if the Kc may move to the right, meaning faster conversion, and the Ke may move upwards, which means it got faster modulus buildup, but all conventional coatings stay at the lower half of this graph, which means Ke over Kc less than 1. One direct consequence of this sharp increase of modulus versus conversion at the last stage of a cure is the fiber microbending performance, which is critical for overall fiber performance, optical performance. And this will get worse from a rising primary modulus on fiber. From the classic model on the dual layer coating mechanical microbending sensitivity and expressing the primary coatings buffering effect and secondary coating shielding effect. This factor of a Cmech, meaning the coating mechanical property factor, is roughly proportional to the square of the primary coating modulus on fiber. When you correlate a coating property to fiber, you should use the property on fiber instead of on film, which could be very different. So even very small increase of a primary in situ modulus could amplify fast into a higher microbending sensitivity of the coated fiber. And before we start to show our actual new coating kinetic behavior, first, it is interesting to see theoretically how it looks like when this ratio equals to 1 or higher than 1. When it equals to 1, the modulus linearly increases with conversion. And when it is higher than 1, it starts to show a decelerated increase in shape, which means the rising of modulus versus conversion will slow down at the last stage of the curve. And if coupled with a reduction of induction time, and this green curve shows even with the same ratio, now the induction time is reduced, and this curve is further smoothed out into a near flat plateau at the last stage of 20% of a conversion, which is typically the commercial coating cure degrees is at. It should be noted that this conventional curve in red, which means sharply rising in situ modulus versus RU, does not really mean the modulus is sharply rising at the last stage of the reaction time. From the left chart, plotting the with the exposure time, modulus and conversion versus the exposure time, you can see both are slowing down following the first order kinetics. It's just the conversion reached plateau first, while the modulus is still rising. And this is the reason for the sharp rising trend when plotting modulus now versus conversion. Now, after seeing the theoretical curves, it is a question whether the Ke over Kc ratio equals to 1 or higher than 1 can be achieved at all. And this is the key slide showcasing our new generation coating P2, P3, P4 versus conventional coating P1. And not only the conversion cure speed and modulus cure speed of these new generation coatings are much faster, especially the modulus buildup rate, so much more faster than P1, right? Um, and And this is to support the increasing of a draw speed, of course. But even more remarkable is the ISM versus conversion curve, which indeed is showing a linear shape from the P2 and decelerated increasing shape from the P3 and P4. And the new generation primary coating not only moved a lot to the right on the KC, meaning faster conversion, and so much more to the top, which means much faster modulus buildup. And most strikingly, it is now moved over to the top half of the chart, meaning breaking the barrier of this line of KE over KC being 1. And I did not even show the P4 because the P4 is way on the top, having a very high ratio. The benefit with this feature of KE over KC equals to or higher than 1 are very significant. It helps it provides a robust processing window with a very consistent coating properties. And it also helps post-curing stability. And this is very important as during the cable process, such as inking, ribboning, ring marking, the coated fiber will go through additional UV cure. And the primary coating at these process will further increase, and in a lot of situations will even reach full cure, 100%. And the primary in situ modulus of the fiber in the final cable could very well already jumped much higher, even doubled compared to the original bare fiber. And the new generation coating system has been proven significantly reducing this modulus jump after the post-curing, and this is a great benefit to the final cable performance. And with classic kinetic network model prediction based on the statistics of how each type of free radical reacts, the monofunctional monomers building the backbone and only difunctional oligomers building the crosslinks. And only when both sides of the oligomer reacted, one complete crosslink is being built and leading to a small rise of the crosslink density and therefore a small modulus increase, right? And the prediction based on this probability statistics model naturally showing this conventional shape of accelerated increase of modulus versus conversion. And this statistic model did not even use the pseudo kinetic first order assumption, but it still reached the same conclusion and describing this accelerated increasing shape of modulus versus conversion. So then the question becomes, what makes our new generation coating no longer bound by this classic behavior of UV curable coating for optical fiber? We think this has a lot to do with the uniqueness of optical fiber drawing process, with the processing window much faster than any other coating application. Fiber drawing draw towers equipped with well-designed reflectors with the UV light highly focused on the tiny spot of fiber, which means much higher irradiance than any other coating applications. And the higher intensity light results in a very fast reaction, and the fast reaction creates extensive heat as exotherm. And and plus the fiber drawing speed, when it goes very, very high, the glass fiber becomes very, very hot. And the fiber temperature can easily go even above 100 degrees C. And that also contributes to the fiber temperature during curing. And so from photopolymerization process point of view, both intensity and temperature will have major influence, first on the reaction kinetics, second also on the cross-linking network structure, and subsequently coating mechanical properties. For the effect on kinetics, we used a custom-made instrument coupling together a real-time NIR with a real-time DMA, so that we can monitor simultaneously conversion and modulus in real time at the set temperature. It is not a surprise that at high temperature, both the conversion and the modulus buildup rate will decrease. You can see the arrow pointing down from 50 to 100 degrees C. Because the side reactions are occurring more at the high temperature. What's special is the new generation coating P4, which is this green arrow, decrease much less than the conventional coating P1, the blue arrow. This means the new generation coating is less sensitive to the temperature. However, when plotting the modulus versus conversion, the P4 is in exact same shape as the P1, still showing the classic shape of accelerated increase. Very different from what we are showing from the draw tower simulator. We actually also anticipated this because these real-time methods are in extremely low intensity. They are in milliwatts level, so nowhere comparable to the actual fiber drawing conditions. Nevertheless, this experiment does show the temperature effect from 50 to 100 degrees C, where the direction of these arrows pointing to, the ratios of a Ke over Kc, which are labeled here, are all going slightly higher. And this means less drop of Ke than Kc at higher temperature. And this is an indication that the fiber drawing process, where the fiber temperature during curing can be as high as 100 degrees C or even more, likely to have a higher Ke over Kc ratio, and that makes it maybe makes it possible for reaching or exceeding 1. And the high temperature and high intensity also have a significant effect on the network structure. Under normal condition of a moderate intensity and temperature, the network is supposed to be is really rather complete, and the chain ends, some of the chain ends that showing here are normal because all chains have intrinsic chain lengths, not infinite. But under a high intensity condition, the free radical concentration increases, causing the termination rate to increase. And in the meantime, under the high temperature, side reactions takes place more. And both the high intensity and high temperature causing some chain ended earlier. So it will end up having a lot more network defects, like many more network defects, chain ends, dangling chains, and the consequence of these network defects is the coating modulus on fiber is always lower than film modulus. And this is a very well-known fact in the industry. But to prove this in the lab, we custom-made this curing system having LED lamp with a mirror design achieving very high intensity at 20 watts per square centimeter, much higher than typical conveyor system, and the hot stage that can control temperature all the way to 150 degrees C. And this chart with 5 example coatings, all showing the same effect, that the film modulus with this high intensity device, but set at the 25 degrees C temperature, purple bars, they are lower than the typical conveyor system modulus, the blue bars on the left. And then when the temperature rises to 100 degrees C, it further drops to the red bars. And the modulus level in these red bars in all these 5 examples is now closely matching to the modulus on fiber, which are the green bars. So we assume this suppression of the plateau modulus on fiber and caused by the high intensity and high temperature could very well have contributed to the higher Ke, because Ke is the relative modulus buildup rate constant. with all these complex factors in play, much more complex than a simple conventional concepts of fast cure. It definitely takes a much more advanced design of coatings to make the Ke over Kc ratio, breaking the barrier of 1. Although our study was using a draw tower simulator, it is intended only to be a simulation tool. In the end, the ultimate proof of processing robustness needs to come from the actual fiber drawing process. And these slides compare 2 glass fiber drawing trials that intentionally set with very wide processing windows. On the left, with conventional coating system, on the right with the new generation coating system. The conventional coating set with 7 different conditions, all tuned to similar UV dose, with lamp number combined with intensity variations up to 3.4 times, and accordingly, speed window also 3.4 times variation. And notice the resulted conversion ranges from 87 to 95, even at these similar dose levels. Without more detailed discussion here, here I listed some simple kinetic explanation why under the same dose, the change of intensity does cause cure degree differences. The new generation coating shows a similar range too, from 87 to 95% of a conversion. However, in this case, it was with a much bigger processing window of a UV dose level not tuned to the same dose. It was intentionally set with 4.8 times of a variation, almost 5 times of a variation. And this came from lamp intensity window of a 2.2 times, speeds window of 2.2 times. But instead of offsetting each other to the same dose level, we intentionally widened the window by having combination of the highest speed combined with the lowest lamp intensity, and vice versa. So under such a dramatically widened window, the fact that the new generation coating still showed similar acceptable range of a percent RU from 87 to 95% really demonstrates its superior fast cure design. But even more remarkable is the in situ modulus versus RU trend. While the conventional coating confirmed following the classic shape of accelerated increasing shape, the modulus buildup, if extrapolating to 100% normalized to 1 for the relative modulus, at 90% of the cure, it only reached 40% of the modulus buildup, which agrees very well with our DTS results. And in a clear contrast, the new generation primary coating shows a very flat, linear curve, almost plateau, with modulus buildup at 90% of the cure, already reaching 80% of the modulus, and this way ensuring a very stable coating property profile, and as a result, very robust fiber performance in the wide window of processing conditions and also after post-cure. So in conclusion, we introduced this new kinetic parameter Ke over Kc, which controls the shape of the relative modulus versus conversion. And we demonstrated our new generation primary coating exhibit breakthrough feature of this Ke over Kc ratio equals to or higher than 1, which significantly reduces the degree of modulus rise in the last 20% of the conversion. And it provides very robust processing windows with consistent coating properties. And we did some mechanism study. It demonstrated it attributed to advanced coating design with faster modulus buildup speed and optimized sensitivity to the unique high intensity and high temperature condition from optical fiber drawing process. And here, the last slide, I'm listing these 4 papers we published in recent 2 years related to our next generation coatings. Here, I'm concluding my talk. Thank you for your attention. And if you're interested, you can scan this QR code to visit our webpage introducing our technology and our existing product portfolios. The new generation coating is not covered here, but please feel free to talk to our business representatives if you're interested. I think, well, according to the time, we are pretty on time and still have plenty time left for the questions. Thank you.
Thank you so much, Huimin. Just so much great technology that has evolved over the years and really has helped to optimize the processing with these the next generation coatings. A few questions have been coming in, and I invite the participants to enter any questions that you might have for Huimin in the chat function. First question is, with the range of curing temperatures and fiber drawing processing conditions with conventional coating systems, have you determined an optimum temperature or processing conditions with these new next generation coatings?
The new generation coatings is designed capable of handling hotter and hotter glass. But in terms of the cure speed, if you want faster cure speed, really you prefer a cooler glass, which traditionally it is 50 degrees C. I mean, your die temperature is set at 50 degrees C. It is only because of at high speed, the cooling efficiency is no longer sufficient. So when the fiber goes into the die, it is still pretty hot, and causing the coating during the curing is still pretty high, much higher than 50 degrees C. That will indeed, in relative sense, reduce the cure speed, but our new generation coating designed with fast cure can handle much better of a hotter glass. But if you talk about optimum, faster cure speed still prefers a cooler glass.
Cool. Yep. Is in the system of lower versus higher temperature, is it possible volatile monomers are lost at the higher temperatures, leading to perhaps enrichment of the dysfunctional monomers and therefore a more rapid modulus buildup?
The volatile in the coating is always existing. I mean, the fact that you see a browning of your coarse tube is all from volatiles coming out, and it's typically get burned out from the microwave curing. And the LED is a little bit more challenging to burn out, but you see evidence of volatiles coming out. And the volatiles coming out can be controlled better with faster cure coating because you build your network faster. Therefore, those volatiles are quickly built into your volatiles are monomers. So your monomers are faster building into the network, therefore reducing the amount coming out. But there will still be small amount coming out, and that can be handled by exhaust system. And from our experience, the small amount of volatiles came out, did not see a dramatic change of our, the final properties. The final on-fiber properties of modulus being much lower is indeed compared to the film modulus, right? Is mainly due to the high intensity and high temperature of the fiber drawing process. It's not because of the volatiles coming out.
Okay. What is the change in micro bending losses, if any?
As the slide I was showing earlier, this new generation coating showing a very stable modulus at the last stage of the cure, which means either you cure to 90% or you cure slightly less to 85%. You still have a lot more room of a conversion, right? And at the post-curing process, it will increase further. So with that increase of a conversion, the modulus typically will sharply increase, and our new generation controlling this increase, which means your final product will be much better controlled on the modulus level of primary modulus, and lower the primary modulus on fiber, better your microbending performance. So this new coating design, if we design for low microbending sensitivity, it will guarantee you much better. You will achieve low microbending sensitivity on fiber.
Right. Is the unsaturation number of the monomers the same between the old and the next new generation coating formulations?
If you measure the conversion on fiber, yeah, you are measuring the overall conversion, right? You cannot tell the conversion is it from monomer or from oligomer. The overall conversion of our new generation coating, if you set your processing condition exactly the same, you should see the new generation coating will give you a higher conversion number because it's faster cure now. Just as the P1, P3, P4, and it's all much faster than P1, P2, 3, 4. Yeah.
Yes. And here's one last question. Have you actually drawn fibers with this next generation coating and measured the microbend performance and also a strength analysis to determine the end value of the fiber?
Yes, yes. Actually, on the last paper is our paper presented here, focusing on kinetics. All the other three papers, they were presenting overall properties that included the microbending performance, measured by two different methods that are very popular. Method B, sandpaper test, measuring the room temperature microbending performance. Method D, basket weave, and particularly showing you a low temperature microbending performance, all presented in some of these papers. I believe the number 3 was showing those results. And the fiber strengths, the ND value measurement from both the 2-point bending and tensile strengths were all presented. And they are all showing excellent properties.
Yep. And the paper references that Huimin is just shown here are available through the IWCS website.
And 2 more papers this year, you will see more and more about the new generation coating properties on fiber.
Fantastic. Yeah, we look forward to that very much. One more question just quickly came in. Is the new generation coating SVHC free? For example, the TPO photo initiator.
Yes, yes. If you read the title of the number 3 paper, it says fast curing next generation primary coating designed around regulatory landscape. Yes, all new generation coatings are now in full consideration of the new regulatory requirements.
Fantastic. Well, I appreciate all of the questions that have come in and the participation here of the attendees. I do want to make sure that each of you are aware of Huimin's contact points, her email address here, if in case you want to reach out to her with any additional questions. And again, certainly you can review this webinar once again or share it with your colleagues as it has been recorded and will be archived on our IWCS.org website. Our next webinar event will actually be next Wednesday on April 22nd. Eastern Time. It will be a industry trends webinar from Dow. And then We also have coming up next month a technical paper webinar by Proterial on Friday, May 15th. Each of these webinars are at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for these webinars. And of course, please feel free to share these with your colleagues so they can join in and register as well. Again, I want to thank Huimen for all of her energy and contributions to this excellent work and the evolution of very important optical fiber technologies as we move forward into the brave new worlds of AI and quantum computing and data center technologies. So again, thank you to you and Covestro. And I do want to remind everyone here that, again, coming up next Friday is our deadline for receiving abstracts for technical papers such as this to show the important work and innovations that you and your company have been generating, provides excellent recognition for that work. And it's a very simple process to submit an abstract. So please consider doing that if you've not done so already. We've received a good number of abstracts so far, so it's going to be a very, very vital and great conference coming up to celebrate our 75th anniversary in November. Again, I also want to recognize and thank some of our leading partner sponsors. And not only do they provide generous contributions to IWCS to allow us to bring these important technical innovations and information to you and our global community, but also the technical content that they clearly provide to us. So again, thanks to these leading suppliers in our industry for your generous support. And again, coming up on November 1st through the 4th in Orlando, Florida, we're heading back to the Gaylord Palms to celebrate our 75th anniversary. There will be some really memorable events. So consider coming not only to present your work, but perhaps bring your family as well. There'll be a lot of fun both within the conference, but also clearly there's a lot of new rides and exciting events at both Disney and Universal, and so could be a good time to bring the family as well. So again, stay tuned to your inbox and also on our website for more information on what's going to be happening in November. So again, we want to thank you for participating today. Have a wonderful weekend and look forward to having you with us next week and beyond in this webinar series. Take care. Thank you.